Welcome to this tutorial on understanding the product of two Gaussian distributions. We will revisit the base formula, and the requirement to multiply two Gaussian PDF arises from this formula. As you can see that in the numerator of this formula, we have a likelihood which is Gaussian distributed, and we also have a prior which is Gaussian distributed. The small p here denotes probability density function and not a discrete probability because x is a continuous random variable and z is the measurement of that particular noisy measurement of that particular random variable. So the multiplication requirement comes because of this numerator, and in many Bayesian applications we assume the probability distribution of both the likelihood, that is this part, and the prior as normally distributed. So this is the formula for probability density function of normally distributed variable, where mu is the mean and sigma is the standard deviation. So now basically what we are assuming is that both this likelihood and prior are following Gaussian distributions, and they are independent of each other, and we are multiplying these things together to come to this posterior. This denominator is just a constant. Actually, it is called evidence, and for all practical purposes this can be omitted. So we are assuming now here this is our likelihood and this is our prior, and we are saying that it's a normally distributed PDF with mean mu1 and sigma 1 as its standard deviation. And just for the ease of nomenclature, we are going to name it as a function fx. And similarly, we are also assuming that the prior is also normally distributed, and it has a mean of mu2 and a sigma of sigma 2. And both these functions are independent of each other. Both these distributions are independent of each other. And for the simplicity's sake, we call this entire function as gx. So before we get into the multiplication of fx with gx, let's try to understand how this whole function works. So essentially, the formula for Gaussian distribution is as shown on the slide, and what we are seeing here is that this particular component is just a constant. It doesn't contain any term of x in it. Everything 2 pi is a constant, square root operation results in a constant, and sigma is also a constant. So this is just a, you can call it a scaling factor for this exponential. So this is just a constant part, and this exponential function actually contains the random variable x. So we will look at this particular expression in more detail and try to solve this. So here we are we have taken out this function here, and we are expanding this numerator here. So if you open these brackets, it will be x square minus 2 mu x plus mu square divided by 2 sigma square. And idea here is that we want to solve this equation to get it in quadratic form, something like this: ax square plus ax square plus bx plus c. And then through these coefficients of a, b, and c, we should be able to derive the formula for the mean and sigma. So once we have expanded this numerator, we are going to divide this all these three terms with 2 sigma square and rearrange it. So if you see, this x square term has a coefficient 1 by 2 sigma square. So let's call it a. So this becomes ax square. And similarly, we have 2 mu divided by 2 sigma square, and these two cancels out. And what we get as b is mu by sigma square. So this is the b part. And similarly, this mu square is divided by 2 sigma square, so this becomes c. So as you can see now, this entire expression here is expressed as a quadratic in the quadratic form, and we are doing it for a special reason which will become clear in the subsequent slides. So we basically solve we solve for as I've shown earlier, that a is 1 by 2 sigma square. So this is what is the expression, and what I've done is I have calculated the value of sigma in terms of a. So this is what it looks like. Sigma square can be expressed as 1 by 2a, which is the coefficient of square term, x square term. And similarly, if you see, b is nothing but mu divided by sigma square, which is exactly what is given here. And I just shift this term here to calculate to get the expression for the mean part. So mean becomes b multiplied by sigma square. Sigma square we have already calculated from here. In fact, you can actually write it as b divided by 2a as well, which is the same thing. So there's a reason why we have brought this equation in this form. Just to recap, this first part is just a constant which is just scaling this exponential, we have expanded this expression and got it into quadratic form, and through that quadratic form we have expressed its sigma and mean in terms of the coefficients of this quadratic equation. So let's now multiply our fx and gx together. Recall fx has got a mean mu1 and sigma 1, and gx has got a mean mu2 and sigma as sigma 2. Both of them are normally distributed and are independent of each other. So here they are. This is the expression. As you can see, I have color coded mu's and sigma. So for fx, as I said earlier, mean is mu1 and sigma is sigma 1. And for gx, it's the same thing. It's the opposite, which is sigma. In fact, there should be 2 here, sigma 2 and mu2. And we are going to multiply these two together like this. So fx multiplied by gx. Essentially what we are trying to simulate or calculate is this product here, the numerator of the base formula. So when we multiply these two terms together, again, this term and this term, when multiplied together, will give rise to this term, which is again a constant and is just scaling this exponential. The inner part of this exponential contains this expression. If you recall, if we have any exponential which is raised to the power x and it is multiplied by any other exponential which is raised to the power y, we can write this whole thing as x plus y, which is what is given here. So this is the central piece. As you can see that this, even after multiplication, this whole formula is resembling the Gaussian distribution, which is a very important point, because even after multiplication, the posterior retains the Gaussian form, though the mean and its sigma varies. So again, this is just a scaling factor, and we have to concentrate on this exponential part. And again, we want to reduce this entire equation into ax square plus bx plus c kind of a form, so that from its coefficients then we can calculate the new mean for the function hx and new sigma. So we expand these brackets, these numerators here, and again this numerator is also expanded, and then we add the terms which are same in power. For example, x square term here and x square term, they will get added, and we come to a coefficient which is 1 by 2 sigma 1 square plus 1 by 2 sigma 2 square. Then we take out the x part here and x part, and we club those terms together, and we get 2 mu 1 divided by 2 sigma 1 square plus 2 mu 2 divided by 2 sigma 2 square, and it is multiplied. This is the power of x. And lastly, we are going to club these terms together. So this is what mu 1 square divided by 2 sigma 1 square plus mu 2 square divided by 2 sigma 2 square, and let's call them again a, b, and c. These are the coefficients of this equation, which has been reduced to quadratic form. And since after multiplication hx is retaining the Gaussian form, so we can deduce from the previous formula, that is the one shown on the slide, that the new mean of this hx is nothing but, so the new mean, a new sigma for the hx, I call it sigma h, is nothing but 1 by 2a, and this has come straight from our previous formula that we calculated here. And mean will be, mean of h, new mean for h will be b multiplied by sigma h square, which is what I have shown here. So first let's calculate the a. A is given, if you see here, a is 1 divided by 2 sigma 1 square plus 1 divided by 2 sigma 2 square. So I take this from the equation itself, and I multiply 2 to it, because I have to have this 2a, and when I multiply by 2, all these 2's they get cancelled out, and this results in this expression, and then I just take a reciprocal of 2a, which results in this, and after few simplifications, the formula for the mean of h is this one. So one immediate observation that you can make here is that sigma h will always be lesser than both sigma 1 and sigma 2 because of the nature of this expression. These two terms are getting multiplied in the numerator and added in the denominator. As a result, this expression will be, the final result of sigma h will always be lesser than sigma 1 and sigma 2. It has a very big repercussion. What we are basically trying to say is that when we multiply likelihood by prior, the uncertainty in posterior reduces. because its sigma is reducing, and hence this filtering action is taking place. We will take this expression of sigma h, and then we will calculate the mean of h. Essentially here we have already found out sigma h, so we just multiply it by b, and b is this term. If you recall, b is this term here. I've just copied it and then multiplied by sigma h square. This is sigma h square, and I then simplify this particular expression here, and which results in cancellation of the denominator of this and the numerator of the second term. And after some rearranging, we get mean, that is a result of the product of fx and gx. The mean of that is this expression, and this is a very interesting expression. A special case of this is that if our sigma 1 and sigma 2 are the same, then our mean, new mean, is nothing but the average of the means of fx and gx. That means equally weighted. So if essentially if I had a probability distribution function here with say mu1 here, mu1, and its standard deviation was sigma 1, and I have another probability distribution function here which is mu2, and it is again having the same sigma. Essentially sigma here and here are same. Then what this formula says is that the new Gaussian will be somewhere in the middle of both the means, that is here, and since its variance is going to be lower than both these sigmas, hence it will be a peakier PDF like this, and the mean will be in the center of mu1 and mu2. So this is a very important observation. In the next section we'll understand the Bayesian filter.